Okay, so we continue. So this takes up the place. So this is the inlet volumetric flow rate multiplied by density, which will be this equal to this one here, the one that we've been using originally, which is this one, isn't it? Then why is it 0 on the end here? Why do we have ML? Do we have an outlet? Do we have output mass from our question? I don't think we do. And here is why. Because it says that the beaker was filled with water, isn't it? It didn't say that there was an overflow of water, did it? It did not. So if there was an overflow of water, if the tap was full and the beaker got full such that water began to overflow, then would have ML. Otherwise, ML becomes equal to 0 because the beaker was full, that we just told it was filled. And that's it. So there are something that when it got full, the tap was closed, isn't it, at this moment? The moment that we've captured is where it's gotten full. The beaker has gotten full and nothing has spilled over. So that spillage is what becomes our ML. So in this case, because there's no spillage that what has been talked about, ML becomes equal to 0. So input minus output becomes 0, plus production. There's no production of water that is happening in the beaker. As you can see, we've not been told, isn't it? It's just water that filled in and that's it. There was no reaction that happened here in this single component system where there was water being released as a byproduct or anything like that to increase the volume of water. It remains the same. Okay, so now we move to our assumptions. Now we make assumptions for the system. We've already begun making them actually from our mass balance. So the first assumption, you always have to write the assumptions before you calculate. You calculate based on assumptions after all. So you need to justify that. You need to place those assumptions first. So the first assumption we're making is that there's no outflow of water. So this is actually it. Based on the information that we've been given. We can actually call it a fact, but we'll call it an assumption. No outflow of water. Okay, so meaning F outlet, this should be a small letter there. Should be yeah, down there should be small letter L. So meaning volumetric flow at the outlet is equal to 0 because it says the beaker is full until the beaker is full. The second assumption is that there's no production of water in the beaker. So meaning therefore our P is equal to 0. Okay. Then the third step is to find the solution using integration. However, this I feel is not necessary. But then for the sake of understanding where the formula is coming from, maybe you can look at this in your time to try and understand it. But what you need to take home is this one. This is the one that we're looking for. So how we got here, maybe you can take time after this lecture to just try and understand how exactly we got here. First from integration there with the limits there as H and H0. So H0 is obviously 0. This is before there was water in the beaker. And now when the beaker got full, that's the H we're talking about here, the DH here in question. Okay, and time is of course before there was water. And then now when the beaker got full, that's time that was recorded. Cross-sectional area and volumetric flow rate you are given in the question, changing time. So in the end, what we achieve H in terms of as a function of time. So height as a function of time is equal to initial height, which is H0, plus volumetric flow rate at the inlet or input divided by cross-sectional area or surface area of the beaker multiplied by time it took to fill that beaker. So this is what you carry for a single component system. This is the equation. This is your working equation that you use. So during the test or exam, you don't necessarily have to carry this. Initially, I would let students carry this, but it would be so difficult for them. So I just thought, I think just carry this. This is important as long as you're able to understand by yourself exactly how we got here. So now that becomes our working formula. Okay, so now this is how it's going to look like. So you have that, and then in terms of a graph, This is the understanding. In terms of a graph, this is the understanding. You have time, isn't it? So it took 10 seconds to fill the beaker, isn't it? So the height, this is height on the y-axis, and the x-axis has time. So as the beaker was filling, as you can see, it's a straight line, it's a linear graph. So as the beaker was filling, it was over time, isn't it? So you have that rise in the H till it reaches a certain H, isn't it? After 10 seconds, that's the H we're interested in finding. So after 10 seconds, that height was reached, isn't it? So meaning, going forwards, what does FL is equal to FI mean? Going forward beyond this point, when there's now an overflow, okay? So this point where it got full, it's at 10 seconds. So it means that at 10.1 or 10.01 seconds, what happens? You begin to notice an overflow. So imagine you go to your sink in your house, you place a cup under your tap, you open the tap. So initially the cup will be empty, isn't it? Then over time, when you switch on the tap, obviously as time passes, seconds will be passing, the cup is filling at a certain volumetric flow rate. Then the cup gets full. Then if you don't close the tap, what happens? It will begin to, the water will begin to spill over the cup. So at the moment where the water begins to spill over now, it means that your FL will be equal to your FI. So meaning your volumetric flow outlet will be equal to volumetric flow inlet. How many agree?
Say that again.
Volumetric flow of your input or inlet will be equal to volumetric flow at the outlet.
At that instant when it's 4 years.
When it's full, yes. Do we agree? Do I need to repeat that expression? Because it's very important going forward.
You can repeat, madam.
Okay, so what we're saying here by the volumetric flow of the tap, isn't it? From the tap, that water from the tap, the rate at which that water is coming into the cup, that rate is equal to the rate of the water leaving the cup and spilling over. That's what we mean. So you can try and do that simple experiment even in your house. After this, you open the tap. So when the water gets full, basically, you know how water behaves, isn't it? Even like, there's a way that the atoms will hold together on the surface. So basically, the water will just be splashing and going out. So basically, what's coming in from the tap will just bypass the cup and just flow out. So that rate will be the same because the cup itself is full. So basically what's coming is just going straight to leave the cup. It's just landing on the surface and pouring, spilling out. That's what we mean by FL is equal to FI. So please, you need to remember that concept because going forward, we're going to use it time and again. Time and again. Okay, so now.
Madam, I've got a question on that same one.
Yes.
So you're saying, okay, I was believing to understand that when it's full, at that instant when it's full, the rate of intake and the rate of output is the same. But again, if you increase the input, yes, with overflowing. When you increase, is it going to be the same with the output?
Yes, the output also increase. So meaning the rate of overflow also increase. So if you are overflowing slowly, isn't it? So let's say, okay, let's say your tap has an issue. I have a very annoying tap in my house. I need to fix it. It drips, okay, like it's been dripping bit by bit. Okay, that's water loss. So now if I put my cup under that tap, isn't it? It's dripping drop by drop, okay? Like the volumetric flow rate is like really small, okay? So eventually, of course, after like an hour, okay, let's say after 30 minutes, okay, 30, 20 minutes, the cup will get full, right? From those drops.
Yes.
Then what happens? It also begins to overflow, right?
Yes.
So now what rate do you think is going to overflow? The same rate that the drops are coming in, isn't it? So a
Yes.
drop, it's full, the cup is full. Let's picture that the cup is full from those drops. So the next drop that comes in the cup, what happens? An equal amount of a drop will what? Will overflow.
Will come out as well.
Yes. Drop for drop. Drop for drop. If
regardless of the pressure.
No, we're talking about volumetric flow rate.
Oh, okay.
Yes, so we're including what we call pressure, isn't it? It's included in volumetric flow rate.
Yes.
So meaning if I now slightly open the tap, slightly turn the tap, what happens now with the overflow? It will not remain drop for drop, isn't it? It's also going to dance to the tune now of the new FI. Such that now if I open the tap fully, full blast, what's going to happen to the overflow also? It's also going to just go crazy at the same level. So FL will be equal to FI. Then if I close the tap, what happens? The overflow also stops, right?
Yes.
So the moment the last drop now from the tap drops there and the tap is closed, what happens? That will be the last thing that will come out of the tap, out of the cup, and the cup will, provided it's on a flat surface, and the cup will remain as it is. It will stop overflowing.
Okay, so what you mean is the equalization is instant.
Yes.
Based on whatever you put in. Okay.
Yes. Yes, it's instantaneous. That's the concept we're getting. We're using rather. Okay. Yes. Okay. Any other questions before we move forward? Or is it clear now?
It's clear.
Clear now, because going forward now we'll be
Yes.
looking at concentration. We'll be looking at concentration also. And it's also a bit confusing. Maybe let's add it here. So that when we get there, we just cross over. So it's same with concentration. So if the concentration of what's coming in, okay, will be the same as the concentration of what's overflowing. Provided what's inside the cup also is the same concentration as what's coming. Okay, let me put it this way. We're going to solve these questions also. So I might as well just illustrate from here so that we get it right away. So the illustration I can give is that you have water, isn't it, in a cup? Okay. Let's say it's halfway in a cup, halfway, half-filled glass of water. Then you get a bottle, you get 5 liters mazoe. You begin to pour in the cup. So what's happening to the concentration of mazoe in the cup? So meaning C0, initial concentration of mazoe is equal to 0, right? Because initially there was no mazoe in the cup, it was just pure H2O. Then you begin to, so meaning change in concentration over change in time is what you're dealing with. So meaning concentration will begin to increase of mazoe in your cup, isn't it? So at the beginning, you feel it too dilute, it won't be that sweet. Till it will reach a kind of a level of sweetness that you like. Then you still continue pouring the mazoe. So at that point, that's now it reaches the sweetness that you like. Let's say a combination of water and mazoe that you like. The concentration of that combination of water and mazoe, will it be the same concentration of mazoe in the glass? Would it be the same as the concentration of the mazoe in the 5-liter container? What do you think?
You said, I think the concentration of.
So you have water, then you began to slowly pour mazoe, concentrated mazoe into the glass of water. So as you begin to pour the first few drops of mazoe there, is that concentration in the glass? It won't be the same, isn't it, as the concentration of mazoe in the actual mazoe container, isn't it? The mazoe
Yes.
container will remain highly concentrated. We agree, right?
Yes.
Mm-hmm.
Yes.
Then over time, what happens? You continue pouring till it becomes too sweet. But even if it becomes too sweet for you, there's still some water, isn't it, somehow? The concentration will still be lower than the concentration of the mazoe in the 5-liter container, isn't it?
Yes.
Then it will begin, so you continue pouring the mazoe slowly till the cup becomes full. Then it begins to overflow. You continue pouring. It begins to overflow. You are pouring 5 liters. Do you know that eventually the concentration in the container of mazoe will be equal to the concentration of the mazoe in the glass?
Yes, because the water is going to overflow. You just be pouring the mazoe.
So you end up having more mazoe, isn't it? The water will basically be lost,
Yes.
isn't it?
Yes.
So we understand that, right? So now it means that you reach a point where concentration at input will be equal to concentration in your reactor, which is your cup, and it will also be equal to the concentration of the outflow. We agree, right?
Yes.
Okay. Do we all agree? I need to know that we're all on the same level.
Yes, madam.
Madam Betha,
Yes.
do you agree with the concept? You're following? Madam Bewe. I hope we're following. So now, ideally, what it means is that also another concept worth getting is that as this begins to overflow, the concentration of whatever is inside will be equal to the concentration on the outflow. We agree, isn't it? You continue. So let's say, okay, let's start afresh. You have your half water. Sorry, I think I got signed out there. Let me just quickly share. Are we able to see the lecture notes?
Yes, madam.
All right, okay. So I was saying, as you are pouring the mazoe, before the concentration in the glass even reaches the concentration in your container, whatever will be overflowing will be the concentration of what's the overflow. So FL, the CL, sorry, will be equal to the C0 in here, or the CA as we call it. Isn't it?
Yes.
So another way, okay, so usually students would get confused with that one. But another illustration I like to use is this one. You get your fruticana, put it in a cup. Then as you are walking, you kind of almost trip. And part of that juice in your cup, it spills on the floor, isn't it? The concentration of what has spilled is equal to the concentration of what remained in the cup, isn't it?
Yes, madam.
Okay. I hope everyone else has agrees with what we just said. If there's need for me to explain, please explain again. Please let me know. Because going forward, we're going to need to work with those are the concepts we're going to work with.
Hello,
Hello.
Madam. Me, I'm a bit lost.
Okay, where are we?
I think I was cut off from the meeting. I think on the second step. That's why you are explaining. So all these steps I haven't followed.
And we've talked about a lot.
Maybe if you recorded, it's fine.
Yes, I recorded. I think you just have to listen to the recording.
Yes, I think I'll follow. Thank you.
Okay, all right, okay. So maybe for your sake, I'll just maybe explain this again to say that this represents basically the filling of the beaker with water. So the height was rising, there was a change in height and a change in time. Okay, so there was that linearity that was happening to this point when the beaker became full. After which the height of the beaker does not change, isn't it? The height of, when the overflow begins, the height of the beaker or the height of the water in the beaker remains the same, isn't it? So that's why it's a
Yes.
straight line here. It's represented that it will go straight to infinity. No extension happens. Okay. And also from this point going forwards, volumetric flow, so the flow rate at the inlets is equal to the flow rate at the outlet. Going forward from this point going to the right, that is what happens. So remember that before this point, there is no overflow. So meaning before this point, FL becomes equal to 0. Beyond this point, FL becomes equal to FI. Okay, so this other problem is a bit, this one will need time. I think I'm looking at the next, we only have like 15 minutes left. This one I need to explain very well, and I think we need time for us to go step by step. Maybe let me just share one more thing that could help us. Maybe let's look at a question paper. Okay, so are you able to see the question paper I'm sharing with you?
Yes.
Lazy campus, huh? Okay. So let's look at some of those questions. So maybe let's just use this time since there's not much time left. Let's use this time to just look at how the question paper looks like, how it's structured. So this was for a sessional examination for December 2020. There are 2 sections and 7 questions in this paper. Section A has 1 question. Section B has 6 questions. So for me, I'm not the one who set this paper, but for my papers, section A has 2 questions. While section B has 5 questions. So you still answer a total of 5 questions out of 7, except 2 are compulsory. Why do I do this? Because I like to emphasize on theory as a way of knowing whether or not a student has understood. So I add 40 marks go to theory. So from this paper that carries 100 marks, 40 marks go to theory, while 60 of your marks, 60 marks will go towards calculations. That's how I'll put it. So in this particular paper, there was only 1 question that has theory questions, and it was carrying 20 marks. Okay, so this is section A. So already you can be, from what we've covered today, you're actually even able to attempt some of these questions. So the law of mass action, this one, not this one, but 3. Are you able to see 3? Question 3 here. It says,
Yes.
what comprises environmental process technology? So we said it comprises of what? Environmental processes as well as process technology. 1 mark. So already this one you're able to answer from what we've covered just today. Question 5. List the 4 sectors where environmental technologies are used. Very simple questions. Industry, agriculture, we looked at this. Services and transport, as well as in everyday housework. The question that follows also you're able to answer just from what we've covered. List 2 reasons why models are used. Models are used in order to design and optimize reactors and in order to control processes in reactors. Okay, then this one, define the system in the image. This is the very first system, no, the second last system that we looked at. So those energy exchange, so this is the what? This is an open system. that exchanges energy and exchanges matter with the environment. So even this question you should be able to get right. Define accumulation in mathematical terms. Accumulation is input of substance A minus output of substance A plus production of substance A. That one also you should be able to respond to. I mean, you should be able to answer correctly, including the last question, question number 20. What is included in process technology? Analysis and modeling, we looked at this, isn't it? And breakdown of complex processes into elemental steps. Then a question on mass balance comes in. There's a question here. We'll look at this question also. So this question is a single component question. Okay, the first part of the question is single component because we're only looking at water. So suppose a newly constructed rectangular agricultural pond is being filled with water from a borehole at a volumetric flow rate of 0.5 liters per second. Given that the dimensions of the pond are 10 meters, 10 by 5 by 2, suppose that when the assessment of the rate of filling starts, the pond was already halfway full. Okay, so here it means that initial height is not 0. Okay, this means that initial height is what? Halfway full, halfway of something that is 2 meters high. So it means that initial height is H0 there will be 1. So we'll look at this in detail, don't worry. So use the mass balance approach to calculate how long in days it will take to fill up the pond. Please make all necessary assumptions, give a sketch with boundaries, derive the formula for mass balance equations. A mass balance approach to this problem provides extra information. So you still have the same sketch coming in, except of course this is not ready, this is cylindrical. But anyway, 2 meters high. So you do a sketch, okay, to illustrate the height and the water coming in. So you have your inputs, okay, and then you do the mass balancing. Okay, so for water, it's easy, same as what we did, isn't it? So you have your mass balance coming in, assumptions from this system, there's no outflow of water, so FL is equal to 0, and there's no production. And then equation after integration, so you just pick, remember what I said, you say just pick this final one, this is your working equation. So you pick this one as your final equation. So as you can see, so your H in terms of time there, when it's full is 2 meters. Initial heights, H0 is 1 meter because when you began filling, the pond already had water, it was already halfway full. So you find your cross-sectional area there, volumetric flow rate has been given, then you apply this formula. And you find your H. So in short, you solve for this T, because they're telling you how long in days will it take to fill this pond. So they're basically asking you how long will it take to reach the full height, for the water to reach the full height of the pond. So you know the full height of the pond, it's 2 meters, isn't it? And you know the H0 is 1 meter. Volumetric flow rate you've been given in the question as 0.5. So it's filling at 0.5 liters per second. Cross-sectional area, you're going to get the area of the base, isn't it? So it's a rectangular thing. So how do you find area of a rectangle? It's L times B. So you find 10 times 5 there as 50. So you're interested in finding how long. So your answer here will be in seconds. Why? Because the volumetric flow rate is in seconds. Huh? So your answer there will be in seconds. So you have place everything and you get your answer there, 1.2 days. So this is an example of how this question is solved. So it can be solved. So an example of, sorry, this is an example of an exam question in relation to this topic, single component system, mass balance. I think we can end here for today. Let's meet next week, same time. We'll continue with mass balance.
Okay. Thank you.
All right, thank you, Doc.
Okay, thank you.
All right, you're welcome. Enjoy the evening.
Thank you, love, and good night.
Good night.